Hello everyone, I am Muhyiddin Al-Garni. Today I'll be presenting mixed metal oxides in chemical loop and combustion, reactivity, stability, and pilot studies. This work was done in collaboration with Dr. Mansour Tijani under the supervision of Professor Nader Mahempe. I will start the presentation with a little bit of a background about the process, then describe the aims and objectives of this work, discuss the preparation techniques and the material used, and the kinetic model that was developed based on the experiments, and then moving on into the pilot plan simulation using Aspen Plus. I'll discuss the simulation schematics, reactor sizing, and as well as the results, and conclude with a few remarks. Fossil fuels today make up about 81% of energy sources. And as energy demand increases, greenhouse gas emissions increase, which is mainly driven by industrial processes, power generation, and urbanization. CO2 is the main greenhouse gas where it represents about 75% of total emissions. In the past few years, CO2 emissions have passed 400 ppm. The projections by the end of the centuries estimates about between 600 and 900 ppm based on some models. In order to address the rise of global temperature and climate change, we must eliminate or minimize CO2 emissions to the atmosphere. CLC is an alternative process that allows for the carbon for CO2 capture, as well as utilizing the power from the process for power production. The process consists of two interconnected reactors. One is a fuel reactor, the other is an air reactor. And a metal oxide used as an oxygen, which is the oxygen carrier circulated between the two reactors. In the fuel reactor, where you have a fuel source such as methane reacting with the metal oxide, resulting in carbon dioxide and water. The water is condensed and the CO2 is then ready for utilization or sequestration. The reduced metal oxide is sent to the air reactor where it is oxidized again and sent back to the fuel reactor and thus completing the CLC cycle. For the air reactor, exit stream nitrogen as well as depleted air are the gases coming out of the air reactor. The energy produced from the air reactor can be used for, as mentioned, for power generation due to the exothermicity of the reaction. For the fuel reactor reactions, depending on the fuel used and the metal oxide, the reaction can be exothermic or endothermic. The aims of this work is to develop a material suitable for CLC and develop a model, kinetic model for the metal oxides based on TGA experiment that can be used for a pilot power plant simulation. What makes a good oxygen carrier? There are several factors to consider in choosing a suitable oxygen carrier. First of all, reactivity is the #1 in the selection list. In order to have an efficient and successful CLC process, the reactivity of the metal oxide is very important. And in addition, due to the reduction or due to the cyclic nature of the CLC process, stability and mechanical strength are very important. In addition to selectivity, CO2 and water are the desired product of the fuel reactor. However, carbon monoxide can also be produced in cases of partial reactions or partial combustion of the fuel. The other reaction that can take place is the carbon deposition on the metal oxide, which can lower the material's reactivity. Oxygen capacity, having a high oxygen capacity for the metal oxide can result in lower amount of material needed and therefore minimize or reduce the size of the reactor. And finally, the cost. The cost of oxygen carriers vary. For example, iron is a cheap material, and nickel is on the expensive end, and cobalt is very expensive. For synthesis of material, for this process, two methods were used. For the support, was prepared using co-precipitation method, where aluminum oxide, zirconium oxide, and cerium oxides were made using giving equal loadings by adding the nitrate form of each of them into a beaker of water, followed by the precipitation agent. The solution was stirred for 24 hours and left to age for 3 days. After which it was filtered, and the paste was dried at 120 degrees for 8 hours. And then the solution was, the powder was calcined at 900 degrees for 2 hours, which resulted in the metal oxide. For the oxygen carrier preparation, the support oxide, as prepared per the previous method, was impregnated using the incipient wetness impregnation method via nickel oxide. Then nickel nitrates were added to the solution to a beaker of water, followed by the support. The solution was stirred for 24 hours to ensure homogeneity, and the solution was heated for at 75 degrees. After the water evaporated, the paste was dried again at 120 degrees for 8 hours, followed by 2-hour calcination at 900 degrees. The result was the oxygen carrier powder, which was then ready for testing. The nickel oxide loading for this sample was 30%. The other sample that was prepared was nickel oxide on aluminum oxide. In the same manner, nickel was added to a beaker of water, followed by aluminum oxide. For our experimental setup, an HTGA was used with a flow rate of 20 milliliters per minute for our inlet gases. The reductions, oxidation, and the purging cycles in between were of 5-minute periods each. The fuel, the fuel stream was composition was 40% methane, with the remainder being nitrogen. For this kinetic study, the temperature range was between 700 and 900 degrees. The kinetic model for the oxidation reaction, volumetric model, shrinking core model, as well as the integrated core model were investigated, and it was found the shrinking core model the results in a better fit with the experimental data. For the reduction kinetics, was estimated using a model that was developed by a research group in 2015. In this equation, Tx is the residence time, Ko is the frequency factor, E is the activation energy. Gx is the conversion dependent function, which is neglected when the reaction rate at a constant conversion is only a function of temperature. For model validation, here we see the shrinking core model compared with the data on the right-hand side, we have the reaction rate versus the conversion. After 50% conversion, we can see the model provides a very close estimation in comparison with the experimental data. At the beginning, however, we can see that the model overestimates the rate. And on the left-hand side here, we can see we've reached about 90% conversion under 1.5 minutes. This suggests that our oxygen carrier is highly reactive, which is needed for CLC process. These are the kinetics parameters obtained from the models and was used for the pilot plant studies. The process flow diagram for the methane fuel CLC process, as shown in the figure, consists of two main units: an air reactor unit and a fuel reactor unit. The air reactor unit is made up of the air reactor, a cyclone, and a power generation. The cyclone is used to separate the solids from the gas and then sent to the air to the fuel reactor unit. The fuel reactor unit similarly is made of a fuel reactor, a cyclone, and a power generation unit. The only difference is the addition of a separator, which is used to condense the water from the CO2. As can be seen here, the solid is circulated between the air reactor and the fuel reactor after it was separated by the cyclone. For our model assumptions or the simulation assumptions, gas is in plug flow. We're assuming homogeneous solid mixing, isothermal fluidized bed, dry air for the air reactor, as well as steady state conditions throughout the process, negligible attrition of particles. Only the active sites, because we're using support oxides, we're only assuming that the active sites participate in the reaction. For reactor sizing, the reactor diameters were about 3.83 meters. They're similar cross-section area, 11.5 meters squared. The bed or the solid held up inside the air and fuel reactors were 5.9 and 17.6 tons respectively. The remaining are described the fluidized bed hydrodynamics, with the minimum fluidization velocity being about 2 meters per second for the air reactor and 3.6 meters per second for the fuel reactor. For the results part, we looked into the effect of the fuel stream composition on the conversion, as well as the fuel stream flow rate on the conversion. We can see that the fuel composition matters. The conversion increased from 27% to 74% when we increased the methane molar fraction from 25% to 100% in the fuel reactor. While the molar fraction was kept constant, we can see that the flow rate did not have a significant effect on the conversion, as doubling the methane flow, doubling the flow rate of the of methane only resulted in a change from 69% to 74%. For power generation, for most of the power generated in this process was from the air reactor unit, where about 750 megawatts of power was generated. The consumption for the air reactor unit was 485. Due to the endothermic nature of the fuel reactor or of our fuel of the reaction taking place in our fuel reactor, the more energy was consumed, as can be seen here with 296 megawatts consumed, and the power generation was 100 megawatts, which in total we produced about 69 megawatts for this process. At the end, CLC is a promising technology for power generation and CO2 capture. As can be seen, we can produce power while having a carbon dioxide pure stream. Nickel oxide over aluminum oxide, zirconium oxide, and cerium oxide with a 30% loading was prepared using the wetness impregnation technique, while the support oxide was prepared using the co-precipitation method. The sample was tested in a TGA for kinetic investigation. And then the model that was obtained was used in a pilot CLC case study to produce 69 megawatts. I would like to thank Professor Nader Mahempe for his supervision, and Dr. Mansour Tijani for his collaboration, and every member of the Energy and Environment Research Group at the University of Calgary. I would like to thank our financial sponsor, NSERC IRC program, Canadian Natural Resource Limited, and acknowledge our partners, PTAC and CanMet Energy. Thank you for your time.